Molarity, moles of solute over liters of solution. This is represented by big M. A shortcut or an abbreviation that we use quite frequently, you'll see it in your textbook as well, is a bunch of, or 2 square brackets. So when you see that around something, what that means is concentration of. So for example, we can say the concentration of NaCl, right, just by putting that in square brackets, and let's say that it is 0.5 M. All right, so often what is one of the most challenging parts of looking at and interpreting the concentration in terms of molarity is just what this actually means, because that is really, really important. You're going to be using this to solve all sorts of calculations down the road. So big M, molarity, means moles of whatever the solute is per liter of the solution. All right, so if we're looking here at sodium chloride, 0.5 M, 0.5 molar would mean 0.5 moles of sodium chloride per liter of solution. Right, so that M here, big M, means this part of it, moles of whatever the solute is per liter. So it relates moles to volume in terms of liters, always, whenever you see that big M. All right, so knowing what that means now, we can go ahead and do some calculations. All right, so now we're asked what is the molarity of 0.500 liters of sodium hydroxide solution if it contains 6.00 grams of NaOH. All right, so just as we saw with the gas laws, a lot of times, you may not have a clue of where to start with questions like these. A good place to start would be to just list what you have and what you need, so you can sort of figure out at least a basic way or some sort of a pathway we can use to get there. All right, so we're told that we have, or we're given, 6.00 grams of NaOH, and show what's going on here. NaOH. Oops, I think my computer has a virus of some sort. 6.00 grams of sodium hydroxide, right? And we need the molarity. We're also given that we have 0.500 liters of the solution. Okay, molarity. What does that mean again? Moles of solute. Okay, so what's the solute in this case? The solute here is the sodium hydroxide, NaOH, divided by the liters of solution. Are we given moles of the solute?
No.
We're given grams of sodium hydroxide. Can you convert grams to moles? Yeah, should be a lot better at that now than you were 2 weeks ago. All right, so we're going to convert grams to moles. And in order to do that, we're going to use the molar mass of NaOH. All right, that's the connection between grams and moles, moles and grams. And then the second part of the molarity is the liters of the solution. Well, we're given that. We're told that we have 0.500 liters of the solution, right? So the only thing we really need to calculate here would be the moles of sodium hydroxide. All right, so it's kind of worked out for you here. The molar mass of sodium hydroxide is 40.00 grams. Hydrogen is 1, oxygen is 16, and sodium is 23. Right, so you add those together, you get 40 grams per mole. That's the molar mass. And as we've seen with the molar masses, we can set up our two conversion factors depending on what it is that we need to cancel. We're given grams, we want to convert it to moles, so we're going to divide by the molar mass, divide by 40, and that gives us 0.150 moles of the NaOH. So now we can stick that into our equation or our relationship. So then our molarity then is the number of moles, 0.150, divided by the volume in liters, which was given as 0.500 liters. So the concentration of this solution then is what? .15 divided by 0.5. Sounds like it should be around 3 or 0.3. Can somebody help me, please? 0.03. 0.3. 0.3. How many sig figs? Well, this has 3 sig figs. And this has 3 sig figs, right? We're just dividing, so it should be 3 sig figs. So it should be 0.300 molar sodium hydroxide. Right? So in order to do these types of calculations, you need to know what M, big M, means. Moles of solute per liters of solution. And if you're not given those units, convert them to the right unit. Right? We know how to get to moles. We know how to convert other units of volume to liters. So you just need to get to those two things to get your molarity. So the relationship that molarity gives us, moles of a solute per liter of solution, is something that we can use as a conversion factor to allow us to convert between those two different units. But it's the same type of a relationship that we get from the other conversion or the other concentrations as well, right? We're just going to focus here on the bottom part of this, but the idea is the same for the percent concentrations as well. So if I tell you that a solution is 6 molar HCl, right? What that means, and the way that you should interpret that is, you have 6.0 moles of the HCl per liter of solution. Right? So you're extracting from that concentration a conversion factor. And what can you do with that conversion factor? You can turn it upside down depending on what unit it is that you want to use or cancel out. So we have, for every liter of solution, we have 6.0 moles of HCl. Right? This is just another way by which you can come up with those conversion factors. It doesn't have to be a metric relationship, although we've seen several of those. It doesn't have to be a molar mass relationship, although we've seen several of those. Right? It can be other places where we can derive those conversion factors from. The molarity is one of those places. All right, so let's take a look at an example. We're going to jump down to the last one here. This is quite an involved one, so we're going to walk through this together. So it says how many grams of AlCl3. What's the name of AlCl3? So first name is aluminum, or aluminium. Last name? What's chlorine as a last name? Chloride. That's it. You don't need the tri because this is not a covalent compound, right? You only use the prefixes for covalent things. which is where you only have nonmetals. Aluminum is a metal, ionic naming. All right, so how many grams of AlCl3? So let's just write that down. We need grams of aluminum chloride. I needed to prepare 125 milliliters of 0.150 molar solution. So we're given 125 milliliters, and we're also given 0.150 molar solution. So based on what's given, the volume and the concentration, we need to somehow get to grams, get to the mass of this thing. So let's make a little bit more sense of what we're actually given. So 0.150 molar solution, what does that mean now? So if I told you you had 6 molar something, it was 6 moles of the solute per liter of solution. So if I have 0.15 molar of something, what would that mean? That means I have 0.150 moles of whatever solute it is. In this case, it's aluminum chloride for every liter of the solution, right? This is often the biggest stumbling block in these types of problems. How do you actually make the concentration, how do you turn it into a form that's useful? Well, what does the molarity actually mean? It's moles of solute per liters of solution. So we're going to use this. We have to at some point. Do we have a liter of the solution? Do we have 1 liter of the solution? Are we given 1 liter? No, we're given milliliters and 125 milliliters, right? So it would make sense in order for us to use that molarity to have everything in the same unit, right? This is in mils, this is in liters. So we can convert our milliliters to liters, and that's something that you should know how to do at this point. What's 125 mils in liters? 0.125 liters, right? How did you get that? Divided by 1,000. Okay, so that'll be 0.125 liters of the solution. So we're told how much of the solution we have. We've converted it to the right unit. And we're told what the concentration of the solution is that we're dealing with. So we have volume, and we have the concentration. In any of those two things, are you given grams? Do you see grams anywhere in that? Do you see anything in those two relationships, though, that would allow you to get to grams? Is there something in there that you can convert to grams? What? Moles, right? So even though you don't see the grams explicitly, there is something in there that you can convert to grams, which is moles. So even though you can get to grams in one step, it may make sense to get to moles first, right? So we said that our concentration relates moles to volume. We'd want to get to moles first. So let's start with what's given. We're given our concentration, 0.150 moles of our AlCl3 for every liter of solution. Okay, I didn't do any calculation to get that. I just interpreted the concentration in terms of what it actually means. And I can multiply that now by my volume. Now, why do you think I'd want to multiply it by my volume? Because, yeah, we just said that, you know, even though we can't get to grams, we can get to moles first. In order to get to moles, we would need to cancel out the liters. So we'd multiply it by our volume in liters. And once we get to moles, we can convert moles to grams for AlCl3. Right? Because if we have a periodic table, you can calculate the molar mass of aluminum chloride. Right? So 1 mole of it. So we have 1 aluminum and 3 chlorines. So, help me out. Chlorine is 35.5 times 3, so that's 105 plus aluminum. What's the molar mass of aluminum? 133.3? Confirmation. 3 chlorines, 1 aluminum. Kayan, you're shaking your head, yes? Yeah? You got 133.33 grams of AlCl3, right? We've done this stuff before. We've calculated molar masses before. We're now putting it into this relationship, just like we did previously, so the units are guiding us. We want to end up with grams of our thing, so grams goes on top. 133.33 grams of aluminum chloride for every 1 mole of AlCl3. Moles cancels all the way up here. And we get grams of the solute in this case. Right, so using our concentration expressed or set up in a way where the units make sense together with our volume in the same unit as what we see in the concentration allows us to get to moles. And then once we get to moles, our whole world opens up. Specifically, we can here convert the moles to grams using the molar mass of our solute aluminum chloride. Okay, and what does that give us? Okay. 0.15 times 0.125 times 1. 2.5? 2.50 grams of AlCl3. Right, so there are several steps involved in this particular problem, as you probably noticed. A couple of them are sort of just making sure that we get to the right unit so that it can cancel out. So for instance, converting the mils to liters on top, right? That's kind of old news, but we had to convert it to liters so that we have the same unit that's used in our concentration unit. Right? Once we have the same unit there, we can cancel that out. We get the moles, and then we use the molar mass, which is stuff we saw in the last chapter, to convert it to grams. So again, just to sort of harp on the fact, all we've done here is convert from one unit to another unit to a third unit. Right? It's unit conversions that you're doing using the same dimensional analysis technique that you did way back when in chapter 2. Right? You went from centimeters to meters to kilometers. Right? They were all within the same measuring system. Here we're just going from molarity to liters to grams. It's the same idea, the same general approach. It's just that where we get the conversion factors from is a different thing. half the time, you know, the problem arises from getting set up at the very beginning, right? How do you pull the information out from the problem, right? And the gas laws ones that we practiced with in lab last week are really similar to the types of problems that you've actually seen here, right? You're not going to be told, you know, this is what you have to use, right? You have to figure it out from the problem. All right. So let's jump into one more aspect, one more characteristics of solutions in terms of how we can manipulate them, and that is through a process called dilution. Has anybody heard the word dilution before? What does that mean to you in a non-technical sense? When you dilute something, what is that? You water it down. So if you water something down, what do you explain that to me?
Taylor. Just put more water in it. Like if you, I don't know, say you have a soda and then you have too much ice and the ice melts, then it's watered down soda. Okay,
so watered down soda just has more water added to it. How does it taste after it's watered down?
Gross. There's like no carbonation or anything.
Does it taste as strong as it did at the beginning? So it tastes a little weaker. And when you water it down, what happens to the total volume? The volume increases as a result because you're adding more of the water to it, right? So watering down is a good sort of non-technical way to describe what dilution is. In a more technical way, right, we can say in a dilution, there are several things that happen. First of all, the total volume of the solution increases. The other thing that happens as a result of that, as the volume goes up, the concentration of the solution decreases. What type of a relationship is that? Where one thing goes up and the other one goes down. That's an inverse relationship. Between the concentration and the volume. Okay, we'll come back to that here in a second when we start doing a couple calculations. The third thing that happens, or actually doesn't happen in a dilution, is the amount or number of moles of the solute does not change. All right, so when you water down your soda, the actual amount of the soda stuff that was there did not change, right? You didn't take any away, you didn't add any more soda to it. All you did was just add some water to it. All right, so in a dilution, I should have probably started with this, solvent, which is typically water, is added. And as a result, those three things occur. Volume goes up, concentration goes down, but the total amount of the solute, the number of moles, does not change. Okay. So we can express that relationship just like the other inverse relationship that we saw in lab. Do you recall which of the gas laws was an inverse relationship? Boyle? And what was Boyle's law?
Pressure and volume.
So it was P1 times V1 equals P2 times V2, right? That was an inverse relationship that we saw in class or in lab last week. P1 V1 equals P2 V2. Initial pressure times the initial volume is equal to the final pressure times the final volume. So if the relationship between concentration and volume is the same, meaning an inverse relationship, we would expect maybe that relationship to be expressed similarly to Boyle's law. It should look the same. And it actually does. Right? We can express the dilution equation or the dilution relationship as follows. So we have C1 times V1. So the C here just means concentration. And the V obviously means volume. And then the ones here, the subscript ones, just like they did in the gas laws, just mean your initial conditions, which in this case is the more concentrated solution that we're dealing with. So the product of the concentrate, or the initial concentration times the initial volume, is equal to the product of the final concentration times the final volume, right? So C1V1 is equal to C2V2, right? That's in a general sense, or sometimes you'll see in your textbook M1V1 equals M2V2. Means the same thing. M there just means molarity, right? C here is concentration. You can stick in any concentration unit here, as long as they're the same units on both sides of the equation. So similar relationship to what we saw with Boyle's law, and guess what? Just like we did with Boyle's law, it boils down to, no pun intended, math that you have to do. A little bit of algebra that you're going to have to solve for in the problem. So let's take a look at an example. So it says, what is the final concentration when 0.50 liters of 6.0 molar HCl solution is diluted to a final volume of 1.0 liters? When we had practiced with the gas laws in lab, we saw that when you looked at a problem, there were certain things in the problem that you can focus on to tell you which relationship you were going to use, right? So for instance, if it says you're going to keep the temperature and the amount constant, we're looking at the PV relationship, right? So what's your clue here that you're looking at the dilution equation? What thing in the problem will tell you that you're looking at a dilution problem? It says diluted. All right, that's your clue that you're going to be using the dilution equation. So that then suggests we're going to use our C1V1 equals C2V2. So we have to decide now, what are those things? What's C1, what's V1, what's C2V2, and what is our unknown in this question? All right, so what is a so it's asking us, what is the final concentration? So what is our unknown? C2. This is the thing that we don't know. We're going to have to solve for. What is the initial concentration? What are we starting with? So we have 0.5 liters of a 6.0 molar HCl. Right? So this is the volume that we're starting with, 0.50 liters. That's our V1. The 6.0 molar, that's our C1. And we're told that that is diluted to a final volume. So that suggests that that's going to be our V2 of 1 liter. All right, so this becomes, again, like I said, it becomes a little algebra problem. We need to solve this for C2. The final concentration. So to get, or to isolate the C2 on one side, we can divide both sides by V2. Right, so the V2 cancels out. So we end up with C2 being equal to C1V1 over V2. So then we just substitute our values. don't just put the numbers, but put the units in as well. All right, so we already decided, we pulled out those information, or that information from the questions. Our C1 was 6.0 molar. Our V1 was 0.50 liters. And then our V2, our final volume, was 1.0 liters. All right, so units-wise, liters cancel. That's great. We end up with molarity as the unit. That's what we're trying to solve for, right? Final concentration. So 6 times a half divided by 1. 3.0 molar. All right, so the unit M makes sense as the only unit we end up with. Does the number 3 make sense as well? Well, in a dilution, right, you increase the volume. So it went from 0.5 to 1, so the concentration has to go down, right? And it did, and it actually went down by the same factor that the volume went up. So the volume went up by, it doubled, and then the concentration was halved, right? So that makes sense mathematically, chemically, and then overall, the entire thing makes sense. Okay, that's dilution in a nutshell, right? This is a very, very common technique that's used in chemistry, but in other places as well, to actually make solutions of different concentrations. If you have a stock, really concentrated solution, you can make all sorts of different concentrated solutions if you need to. Okay, questions on dilution? Okay, the last section of chapter 9 deals with an application of solution chemistry. So we'll talk a little bit about this. You're going to see this again in your biology classes, and you'll talk about it in way more detail than we're going to look at here. But I want to sort of pull in an application of this so you see that it's not just, we're not just throwing stuff at you. This is where it's actually relevant. All right, and this is in the process of, or phenomenon known as osmosis. Has anybody heard of osmosis before? Osmosis. How would you define osmosis, just in a general sense, based on what you know about osmosis? Several of you raised your hand, so one of you have to tell me what you know about osmosis. Is that how you study for an exam? You sleep on your textbook under the pillow, you learn by osmosis? That doesn't work. I've tried it. It's not how you learn. Osmosis, anybody? Okay, so we can define osmosis as follows. It's the movement of solvent, which in most cases is going to be water, across some barrier. And the barrier, we're going to give it a special name. We're going to call it a semi-permeable membrane. And you have lots of those in your body, by the way. Lots of semi-permeable membranes that surround each of your cells. They're called cell membranes. Right? They actually keep all of the stuff in the cell inside and doesn't allow things to leak out, because that would be counterproductive. So the movement of solvent, typically water, across a barrier, which we'll call a membrane, semi-permeable membrane. The direction in which water moves, though, is the important thing. So it moves from a region of low solute concentration to a region of high solute concentration. All right, that's how water is going to move always. The driving force for it is a concentration difference across some barrier or some membrane. Without that difference in concentration, there isn't going to be a net movement of water. Right? This happens all the time. Every single day, every single second of every day, there's a movement of water across your cell membranes. But you also take advantage of it on an external sense, right? If you've ever tried to pickle anything, like a cucumber or a fruit or something, right? What do? Anybody tried to pickle anything before? What did you do? A lot of salt, okay. What was the thing you actually pickled? Cucumbers, okay. So you took a cucumber and you put it in a bunch of salty water, basically. Right, so what you did there was you created a difference in concentration of the solution from the inside of the cucumber to the outside of the cucumber. So really salty outside of the cucumber, not so salty inside. And that difference in concentration actually drove the movement of water through osmosis across the barrier of the cucumber. And as a result, what happened to the cucumber? It found itself in a pickle. Right? It became a pickle, actually, as water left. Right? So the movement of water went from the cucumber inside to the outside. Right, and that was because of the difference in concentration of the solution. So pickling is one example of where you apply osmosis, but where it happens on a natural level is when you look at the cells in your body and the movement of water in and out of those cells. We're going to choose one particular type of cell to illustrate this idea of osmosis, and we're going to take a look at the red blood cells. Let's write it in red. The red blood cells. Which are also called RBCs, right? Red blood cells, just abbreviated. Or the technical name for them are your erythrocytes, right? And where do you find red blood cells? In your blood. What do red blood cells do? They carry oxygen, right? So they transport oxygen to the cells that are actively respiring that need that O2, that oxygen. In order for the red blood cells to function effectively, they have to maintain their shape. And what helps maintain their shape is the amount of water that they have in them. So red blood cells can find themselves in different types of solutions. The first type of solution is called an isotonic solution. And in an isotonic solution, that solution is going to have the same concentration as inside the red blood cell. All right, so let's just zoom in here really quick. There's our solution, there's the red blood cell. All right, so the concentration on the outside is the same as the concentration as the inside of the red blood cell. So we said water moves from low solute concentration to high solute concentration. So is there a difference in concentration in this case? No. So in which direction will water move? Well, it's actually going to move both ways, but equally. So there isn't going to be a net movement of water. So water is going to move in, but the same amount of water is going to move out. Right? So there is no net movement of H2O. Because of no concentration difference. Right? So there isn't anything driving the net movement of water in one direction versus the other. And that's kind of what you want to maintain for your cells, right? A perfect environment for them, a perfect solution where water is neither going to leave nor enter in a net sense into the red blood cell. And that's what you want to maintain, you know, through your diet and through exercise and everything else. You want to maintain sort of a constant internal environment, not just for your cells, but for everything else, right? That's part of an overall thing in biology and chemistry called homeostasis, right? Maintaining a constant internal environment. The second type of solution is called a hypotonic solution. And a hypotonic solution is a solution that has a lower solute concentration than inside the red blood cell. Right? Think of one way that I use to remember this is hypo, low. Or hypothermia, right? You have a lower body temperature than what you're supposed to. So in this case, if you were to take a closer look at it, right, there's our solution, there's our red blood cell. All right, so here we have a low solute concentration relative to the inside of the red blood cell, which is going to have a high solute concentration. So in which direction is water going to move? Into the cell or out of the cell? So water moves from low solute concentration to high solute concentration. Right? So water is going to flood into that cell. And as it floods into the cell, what do you think happens to it? It's going to swell. It's going to get bigger, right? So the cell swells. So water moves in. The cell swells and eventually it bursts open. And all of the contents get released. So for all intents and purposes, that cell is dead. It can't do what it's supposed to, which is to transport oxygen. Right? So that process is called Chemo Lysis. Right? Lysis meaning to split, and hemo is for the hemoglobin part of the blood. So the splitting of the red blood cell due to water moving in, the bursting of the red blood cell. So that's in a hypotonic solution, and the opposite of that would be a hypertonic solution. All right, so in a hypertonic solution, this is going to have a higher, so it has a higher solute concentration than inside the red blood cell. So there's my red blood cell. It's in a hypertonic solution. So now, in terms of concentration, the outside has a higher concentration than the inside. Right? So in which direction is the water going to move? It's going to leave the cell, and it's going to move that way. So water leaves the cell. And what's going to happen to that cell then as water leaves it? It's going to shrivel up. So the cell shrivels like a grape becomes a raisin. Or like your cucumber becomes a pickle. That's what's happening, right? You put your pickle in a very, very salty solution. It's very concentrated and it draws water out of the pickle or the cucumber. So for the red blood cell, that process, as the cell shrivels, is called crenation. With an N, right? Not cremation. We're not burning it. It's crenation is what that's called. And if you look under a microscope, it actually looks like a shriveled up red blood cell. Right? It doesn't have the right shape. It's not going to be able to do what it's supposed to, which is to transport oxygen. So maintaining that constant environment for not just your red blood cells, but all the other cells in your body is really, really important, right? Because it affects the movement of water into and out of the cells. Kind of a big deal.
So is that what happens when you have
High blood pressure is slightly different. So that actually results from your blood vessels being constricted from a variety of reasons, right? Usually as a buildup of some sort of plaque inside the cell wall. And it's like if you have a hose and you put your finger over the hose and the water comes out with higher pressure, that's what's happening in your blood vessels. They get blocked or semi-blocked, and then it increases the pressure, which...
So we should try to aim to keep isotonic blood.
Right, so it's not something that you can actively think about doing, like today I'm going to work on isotonic, keeping my blood. No, it's just something that your body does naturally, right, to make it, to ensure its survival. So there are all sorts of mechanisms that your body has in place to make sure that that homeostasis is sort of an underlying theme. Okay, so that brings us to the end of this chapter, which is